This is Unit 5, Lesson 3, Representing Exponential Growth. And this is from Illustrative Mathematics, Algebra 1. Okay, let's look at 3.1. Math Talk, Exponent Rules. Rewrite each expression as a power of 2. So previously you have learned exponent rules where you multiplying like bases, you add the exponents. You multiplying like bases. That means the bases are the same. Then you add the exponents. Okay. When you divide like bases, then you subtract the exponents. When you raise a power to a power, then you multiply the exponents. And I will demonstrate some of these examples. All right, so they want you to rewrite each expression as a power of 2. So if I look at what 2 cubed is, that is 2 times 2 times 2. 2 to the 4th is 2 times itself 4 times. So 4. So remember, when you multiply like bases, you add the exponents. So I would add these and get 7. So this would be 2 to the 7th power. That's how you rewrite it, as a power of 2. So look at the next one. We have 2 to the 5th power, which is 2 times itself 5 times. And then 2 by itself is actually 2 to the 1st power, which is just 2. So then add those. 1, 2, 3, 4, 5, 6. This would be 2 to the 6th. So remember, when you have a base just by itself, it's understood to have an exponent of 1. So the next one is 2 to the 10th divided by 2 to the 7th. So I like to write the division ones as a quotient. So I would write it, the numerator, and then write my division sign or my line underneath, fraction bar, and then write the denominator. So then you can see them together. And this is pretty lengthy to have to write this out. You do not have to do this every time. I just wanted to demonstrate how this works. So that's 2 to the 10th, and then divided by 2 to the 7th. So this is 2 times itself 7 times. And then when you divide, a number divided by itself is 1. So this would be 1, this would be 1, this would be 1, and so on. And then we have 3 left. So this would be 2 cubed, 2 to the 3rd power. And it makes sense because our dividing like bases, you subtract the exponents. Well, 10 minus 7 is 3. So it works. Okay, look at this next one. I'm not going to write this one out. Let's use our dividing like bases. We subtract the exponents. Remember, this is understood to be 2 to the 1st power. So 2 to the 9th divided by 2 to the 1st power would be 9 minus 1. So it would be 2 to the 8th. Okay, so let's look at 3.2. What does x to the 0 power mean? Complete the table. Take advantage of any patterns you notice. So let's look at this table. It's going 4, 3, 2, 1, 0, 81, 27. So what's going on? How do I go from 81 to 27? What is that doing? Well, it's dividing by 3. If I divide by 3 again, 27 divided by 3 is 9. Divide by 3 again, 9 divided by 3 is 3. Divide by 3 again, 3 divided by 3 is 1. And notice these y values here, it's saying their output is 3 to the x power. So this would be 3 to the 4th, which was 81, 3 cubed, which is 27, 3 squared, which is 9, 3 to the 1st power, which is 3, and 3 to the 0 power is 1. Let's look at number 2. Here are some equations. Find the solution to each equation using what you know about exponent rules. Be prepared to explain your reasoning. So I have 9 to the whatever power times 9 to the 7th equals 9 to the 7th. Well, I need this to I need this whole thing to equal 1 in order for this whole thing to equal 9 to the 7th. So this must be 9 to the 0 power. Because look right here, we had 3 to the 0 power, it equaled 1. Okay, let's look at the next one. Look at B. We have 9 to the 12th power divided by 9 to an unknown power equals 9 to the 12th power. Again, we need this to equal 1 so that we end up with our original. So again, this would be 9 to the 0 power because 9 to the 0 power equals 1. Let's look at number 3. What is the value of 5 to the 0 power? Well, we've just seen 3 to the 0 power was 1. We needed this to be 1, so we made it 9 to the 0 power. And then we needed this to be 1, so we made it 9 to the 0 power. So 5 to the 0 power must be 1. What about 2 to the 0 power? Well, same reasons. 2 to the 0 power must be 1. Doesn't matter what you have. If you have 1,000 to the 0 power, guess what? It's going to equal 1. The only one that there is an exception when you have 0 to the 0 power. It's undefined. But every other one, if you just raise anything to the 0 power, it is going to equal 1. Okay, let's look at 3.3. In a biology lab, 500 bacteria reproduce by splitting. Every hour on the hour, each bacterium splits into 2 bacteria. Write an expression to show how to find the number of bacteria after each hour listed in the table. So they're splitting. So at 0 hour, it's at 500. Well, if I split that, it's going to be 500 times 2. If it splits again, 500 times 2, 2 times. If it splits again, times 3 times. Or you could also write it as 500 times 2 to the 3rd power. Okay, what about 6? Notice this was 2 to the 2nd power, this was 2 to the 1st power, this was 2 to the 3rd power. So whatever you're raising it to is what your exponent is, your x value. So 500 times 2 to the 6th power. Now what if the power is t, or the hour is t? Again, if you looked at all of these, your exponent was the number hours. So it would make sense to just have 500 times 2 to the t hour. Look at B. Write an equation relating n, the number of bacteria, to t, the number of hours. So you're basically taking what this is, but you're making an equation out of it. So the number of bacteria equals, so n equals, we're using t as our hour, So take this expression, 500 times 2 to the t power. C says, use your equation to find n when t is 0. What does this value of n mean in the situation? All right, so let's take our equation. When t is 0. Well, what is 2 to the 0 power? It's 1. So 500 times 1 is 500. So what does this mean? Well, at the 0 hour, that was when we started. That's the initial amount. So it's the number of bacteria at the starting time. Look at number 2. In a different biology lab, a population of single-cell parasites also reproduces hourly. An equation which gives the number of parasites P after T hours is P equals 100 times 3 to the T power. Explain what the numbers 100 and 3 mean in this situation. Well, if T was 0, this would equal 1, so 100 would be where you started. So 100 is the number of parasites at hour 0, at the start, the initial amount. 3, just like 2 was up here, 2 was talking about how it's splitting. Well, here they're telling you it's 3 this time instead of 2. So the number of parasites would be tripling each hour. Instead of doubling, instead of splitting, this time they are tripling. All right, so the next one, 3.4, they want you to graph your information. So refer back to your work in the table of the previous task. Use that information and the given coordinate planes to graph the following. A says graph T of n, Tn when T is 0, 1, 2, 3, and 4. And then B wants you to graph Tp when T is 0, 1, 2, 3, 4. So this is your number of bacteria. This is your number of parasites. And on this one, it says if you get stuck, you can create a table. You did not already have a table completed here, but you do have your table completed for this one. So our table, when at 0 hours, remember our number of bacteria was 500. So we would have at 0, 500, that's going to be your vertical intercept. At 1 hour, it was times 2, so it was 500 times 2, which is 1,000. So at hour 1, that's where it would be at 1,000. So you would go to 1 and then up to 1,000. At hour 2, it's going to double again. So this time it would be at 2,000. So at hour 2, we're at 2,000. At hour 3, it's going to double again. So it's 500 times 2 to the 3rd power. So from 2,000, now we're going to 4,000. So at 3, it's going to be at 4,000. At hour 4, we didn't have that on our table, but you're going to double again. So from 4,000, now it's going to double and go to 8,000. So that's what your graph would look like. In exponential functions, it starts out very small, and then all of a sudden it grows very rapidly. The next one, they want you to graph for the parasites. Well, we know at hour 0, there was 100 parasites. So this would be 250, so about right here. I'm going to have to estimate there. At hour 1, they're tripling. So 100 times 3 would be 300 parasites. At hour 2, it's tripling again, so 300 times 3 would be 900 parasites. And then hour 4, it's going to triple again, so 900 times 3 This was 900. Oh, I'm at hour 3, sorry. Hour 3, it's going to triple. So 900 times 3 would be 2,700. And then in hour 4, it's going to triple again. So 2,700 times 3 would give us the 8,100. So here's... So this is what your parasite graph would look like. Let's look at number 2. On the graph of n, where can you see each number that appears in the equation? All right, so remember your number of bacteria was n equals 500 times 2 to the t, and your parasites would be p equals 100 times 3 to the t. So, on the graph, where do we see 500? Well, at the 0 hour, your starting amount was at 500. Okay, where do we see 2? What does that 2 mean for this? Remember, the bacteria was splitting. It was doubling every hour. So the 2 shows us that your number of bacteria is doubling every hour. Look at this equation. 100. Where would you see 100 for the parasites? If you look at the 0 hour, this is the vertical intercept, it's where it's starting. The 3, remember, is telling us how is it changing every hour. This one was tripling every hour. On the graph of P, well, I guess I just answered both of those questions actually. So 2 wanted your just for number of bacteria, and 3 wanted your number for the parasites. All right, lesson summary. So in relationships where the change is exponential, a quantity is repeatedly multiplied by the same amount. The multiplier is called the growth factor. So looking at this one, suppose a population of cells starts at 500 and triples every day. The number of cells each day can be calculated as follows. So here's the 0 day, day 0, it's 500. Then it's going to triple. So it's 500 times 3. The second day, 500 times 3 times 3, or 3 squared. The third day, it's going to triple 3 times, 3 cubed. And then if we plug in d for days, then it's just going to be 500 times 3 to the d power. We can see it changing exponentially, and that p can be found by multiplying 500 by 3 as many times as the number of days since the 500 cells were observed. The growth factor is 3. To model this situation, you can write this equation. P equals 500 times 3 to the d power. That equation can be used to find the population on any day, including day 0. On day 0, plug in 0 for d. Since 3 to the 0 is 1, then it's going to be 500 times 1, and it equals 500. And here is a graph of it. You can see that 0, 500 is right here, and it means that on day 0, the population starts at 500. So that is all for this lesson.